Yeah, so great. Thanks everyone for being here. Today we have Valeria de Paiva talking about Dialectica Petri Nets. So take it away, Valeria.
Thank you, David. So we've forgotten to check if we can move forward, but yeah, we can. So for the people who don't know, today is International Women's Day. And I am going to, I'm saying that it's, you know, to those who celebrate, happy International Women's Day. And my way of celebrating, it's kind of showing you this very, not in my opinion, clever gender pay gap bot, which actually whenever corporates kind of tweet platitudes about the gender pay gap, it kind of shows how bad it is, the gap in the particular place that's tweeting. So it's clever. Move. And I wanted to start by talking a little bit about the reason, well, the reason I think people came up with the idea of the Intercats series, I think was to a large extent due to this. Yes, I suppose I kind of wanted to say thank you to Jules, Toby, and David for inviting me to talk here. And I was going to say that I think one of the reasons why we have this series is because Jules kind of came up with this nice blog post in 2018 talking about lenses and how they appeared in several different places. Actually, I think I'm going to try to see if I can, I don't know. I was trying to see if I could see myself. I cannot at the moment, so you'll have to put up with funny faces. And what I thought I was going to try to do about the lenses for philosophers was to try to come up with my own perspective on that. But you know, things happening in lots of other work interfered, and I then decided to try a slightly different take, which is to show you how some of the lenses ideas have been applied to concurrence theory in a fairly different way. So let me see if this story makes sense to you guys. This is work, I was going to say work with, but it's actually mostly the work of Elena de Lavori and Vilma Leo, who kind of were part of the ACT School 2020 in my group. And my group had some other people who are mentioned there, down there, Chaiyuan Lee, Jade Master, and Aigul Haishel. And I want to thank them all for the work that we did together, which was great fun. And to tell you the truth, Elena kind of gave this talk in 1 minute flat in the ACT 2021. So, you know, I ought to be able to do a reasonable job having 40 minutes or so, but we'll see how that goes. And you know, if you need a visual reminder of everything that I'm going to talk about, it is in this beautiful picture that Elena drew of the nets that we're going to be discussing and how they connect to each other, and the examples in particular that we want to talk about. So this story starts a long time ago, and that's the story about being an accidental concurrence theorist. So this is in white is Carolyn Brown, and this is Douglas Gurr. Doug nowadays is the director of the National Museum of the National History Museum in London, and Carolyn is kind of semi-retired, somewhere nice, and they kind of came up with this original idea of using dialectical categories which were conceived as a piece of mathematics to try to do concurrence theory with it. So how did it go? So we have a chat here, so let me just check, because It is a beautiful diagram, Jeremy. Yeah, I agree. So it started like so. I had my thesis in 1988. I submitted and I only I submitted, defended, but only kind of got a degree in 1990. By that time, Carolyn and Doug had this idea of how to use an idea that was up in the air at that stage, which was that linear logic had an awful lot to do with Petri nets because linear logic uses assumptions, and in a Petri net, you kind of use whatever resources you have, and you produce some other resources. So there was this tantalizing metaphor in everyone's head. And so they kind of came up with a way of putting together the Petri nets morphisms that Glenn Winsco had produced in LICS 1988, with my thesis, which was 1988, and kind of creating this LICS 1990 paper called the Categorical Linear Framework for Petri nets. Then when I looked at that stuff, I said, well, but these nets that you're talking about, which were my original work, they only talked about whether things were connected or not, and they had to call them safe nets. And by and large, I think people, when they are dealing with Petri nets, they want to have multiplicities around. They want to say that you're going to consider 3 engines plus 2 belts and 24 screws to construct a washing machine. So you want to kind of use things with more multiplicities than 0 or 1. So I kind of produced this technical report, Categorical Multirelations, Linear Logic in Petri nets in 1991. And altogether, we kind of written this paper, Linear Specification Language for Petri nets, which was kind of submitted and accepted, but then everyone had gone in their different ways, and we couldn't even join together to do the revisions. So it never went anywhere. This is too far. Hang on. Don't know what happens here, but where are we? Oh, we passed this. No. So yeah, so 30 years later, what happened? What happened was that the Applied Category Theory School asked me if I wanted to do some sort of project, and I suggest this project. And we had this group of 4 people who kind of were supposed to look at this collection of papers that I just mentioned, the old ones, and try to see how this fitted with newer versions of Petri nets that were more in fashion nowadays, things like the work of John Baez and Jade herself, and the work of Joaquin Koch in whole grain Petri nets and stuff like that. And we wanted to put these 2 things together. But actually, I think, it's a bit of a spoiler, but they don't go together so much, and we will discuss it a little bit more in a minute. But so there was renewed interest in the ideas of Petri nets and in the ideas of kind of at least from my perspective, there were some old ideas that I still wanted to see how they pan out, how much people could use them for real, in earnest, instead of just playing with the mathematics. And this is because, as I kind of put a list of theses down there, and all these theses kind of use these ideas of these morphisms of dialectical categories for things that were very, very different. So kind of and of course, Carolyn Brown's thesis is exactly about the dialectical morphisms, but then Johan Lilius put some colors on top of those morphisms, and Vineet Gupta did the variation that everyone knows better, which is the 2 spaces variation. Bernd Fauer kind of came up with a notion of an object Petri net, which kind of uses that notion of Petri net inside another different Petri net and some other work that I don't understand so well. But this is why I'm kind of saying that it was 30 years later, but it was not completely gone out of existence. People kind of carry on using it. And that's why I wanted still to kind of go back and look at it. So this is kind of my introduction, and what I wanted to kind of do today was talk a little bit about Petri nets as I understand them, then talk a little bit about the dialectical construction, the more trivial one. Then I wanted to talk about these constructions on Petri nets that are the beautiful things that Elena kind of produced in her diagrams. And then I wanted to talk about what we decided, or actually Elena and Vilma decided, that is the side of this work that they are most interested in, which is this idea that with the notion of Petri nets that we have, we can put different arcs on the net, and we can have, and that's very different from all the other work that I know in Petri nets, that all the other work that is kind of categorical based cannot deal with arcs of different intrinsic types. So that's what what I'm calling here in the outline different arcs. So the simplest example of a Petri net that I copied from somewhere on the web, it's something like that, where and it's reasonable to look at it, because you might think to yourself, why do I have events and conditions, or why do I have places and transitions? This different kinds of names correspond to slightly different intuitions that the practitioners have, but they're all kind of similar in some ways, because you want to do you want to have two different basic types happening. In this case of this vending machine that I have here, the actions that you do are depositing coins in the machine and then taking off the chocolate bar. So there's two different kinds of chocolate bar. There's the 15 cents chocolate bar and the 20 cents chocolate bar. And there's the several different ways that you can use your 5 cents and your 10 cents, your dime, to construct the amount of money that you need to get one of the two kinds of chocolate bar. And so the point is that you get to a state like this state here, where you actually have in the machine the 5 cents, and you can either deposit another 5 cents and then you get 15 cents, which, no, you don't, right? Sorry, you should. 5 plus 5 is 10, plus 5 is 15. And then you can take your 15 cents bar, or you can take a 10 cents and then a 5 cents, or 10 cents and another 10 cents to get a 20 cents bar. And so the point is that you have actions that change, that allow you to change from state to state, and you have these conditions that have multiplicities, and that can be described in terms of pre and post conditions, which is what Glenn Wenzel said that he wanted to do, and that we followed. So, as I was saying, the squares are events and the circles are conditions, and the tokens move through the net. And the pre and post conditions are on events are the relation-like things that we will treat like we treated them in the dialectical construction. And as I was saying a minute ago, the original version of Carolyn and Doug only had safe nets. So either the relations hold or they don't hold. So hold, we say it's 1, don't hold is 0, and there was no multiplicity. And then when I kind of came up with the technical report, the main idea was to actually add multiplicity by saying that you can think of any relations in set either as a subset of a Cartesian product, or you can think of them as maps, functions from a Cartesian product to the number, to the object 2 in a category, meaning the 1 plus 1, the terminal plus the terminal, and then you can think of that, you can think of how to generalize that using a lineal, which is the next idea. But before that, why we kind of were so excited about Petri Nets that many years later? I think the reason we are excited about dealing with Petri Nets is because modeling is hard, and people seem to like Petri Nets. People seem to like the idea of drawing those things that have actions and movements through the net. At least they think that they liked it when they are starting to think about it. When they start getting gigantic, they don't like it so much and they want the computer to do that for them. But, you know, when discussing with friends, they like this sort of modeling. And you want, I mean, we want things that people feel excited about. Second reason for thinking about that is that concurrence is very hard, and people like Petri Nets. So it is a good way to think about non-determinisms versus causal independence. It makes clear the differences. And as I say, it's all about our users. If there are users who want to deal with that, it's good. Now, there are some downsides to it, right? We have a huge number of types of nets. So as I was saying, colored, stochastic, high order, and stuff like that. And in particular, kind of, I think everyone is going to say to you nowadays that everyone wants the stochastic ones. And we also have a little bit like the issue of the different kinds of lenses in computing. We also have this issue of the different kinds of ways of dealing with probabilities. Trying to use category theory, we have a similar sort of issue. And so, you know, it would be good to try to use problems in concurrency as ways of thinking about problems in probabilities, and vice versa. The different intuitions that one has for probability in using category theory to actually think about different versions of concurrency that make more sense or less sense. But of course, there's a huge number of papers, books, and systems. At that stage, there was a huge natural application for linear logic, and you know, that was a time where people were very excited about the possibilities of linear logic. And somehow the work on the Petri Nets kind of carry on independent of the fashions of linear logic or non-linear logic. They kind of, as I was saying, there's an awful lot of work on probabilistic Petri Nets and in systems that are similar to that, but they are more in the realm of dynamic logic. And as I was saying, the problem at that stage was this idea that at that stage, it was a long-standing problem in the theory of Petri Nets, has been the lack of any clear methodology for producing a compositional theory of nets. And we thought that's what we had, theory of nets. Nowadays, we have a collection of different people with very different directions of how to be compositional about their Petri Nets. But I kind of feel that there is a big dichotomy happening here, which is that most of the other systems of Petri Nets that I know about, they are about one single Petri Net and how it evolves or doesn't evolve, whereas what we'll be talking about, what we're talking in this kind of Dialectica Petri Nets is very different. It's about how, if you are given some nets already, how you put them together to make bigger nets, and what are the combinators that you have on those nets, which is very different from the Bayes and Koch and others ways of looking at internals of the Petri Nets. So I kind of should remind you very briefly about what are the Dialectica categories and how we think about them. And they are very simple in many ways, and particularly this version of the Dialectica. I have a little bit of a problem because there are too many things that are called Dialectica categories, and they are different some of them are very different. It's just that I tend to think of the one that I'm using for this particular case. So in the case of Petri Nets, I am thinking of the categories GC, the variant that was suggested by Girard, and they are simpler than the ones that we normally use for lenses, because they do not have the parameter that the lenses ones have, which were the original ones. So an object here, as I was saying, is two sets, and you have an ordinary set relation between these two sets, and you can think of it as either a subset of U cross X, or, and I was thinking about that as a map into two here, and as I was saying, either you think of alpha of UX being 1 or alpha of UX being 0. And the point that is important, which distinguishes the dialectical version from the two constructions versions, is that we have morphisms from one such object to another such object, V, Y, and beta, and we have the same sort of covariant, contravariant sort of behavior of the morphisms. But while the Schuh construction just then insists on a commutativity of a diagram, we have a more lax version in the Dialectica, one that simply says that there is a two cell from the alpha to the beta, or rather, that the alpha of U Fy implies the beta of Fu Y. So, you think of that as being a two cell between these two relations. And the existence of this two cell it's a bonus, but it's also a bug in some ways, because if you kind of insist on equality of diagrams, you are too strict, and you cannot see some extra phenomena that you might want to see. But it facilitates life, and that cuts down on the number of morphisms considerably if you take the two-like morphisms. And then the structures themselves that the categories have become very different. And that also has been kind of taken back by Mike Schumann recently, or not so recently, in 2008, more or less in 2018, and kind of made much more high order. What I kind of wanted to say right now is that one of the things that makes the Dialectica such a reusable sort of construction is exactly the fact that you can take this object of the category of sets 1 plus 1 and kind of make it and think about an internal sort of version of that by thinking of a lineal. And a lineal is simply, I'm going to be horrible and give the NLab-like definition and say that a lineal is just a symmetric monoidal closed category that's a poset. Because I know that in this kind of place, you can say things like that, and that's what it is. So you just, you can define it by several different ways. You can say that it's a lattice which has, or it's a monoid with an ordered monoid, and give the adjunction bit by bit. And, that's how kind of universal algebraists would do it. And there are several other possibilities of how to get the structure, but what it is a symmetric monoidal closed category that is a poset. And what kind of then will happen is that, you can see that these different sorts of lineals will give you very different structures of your nets. So we call them a lineal. Martin and I called them a lineal a long time ago because of the analogy with quantiles. And the difference between the two is just the quantiles require completeness under limits which we we don't, because we don't, we think that monoidal structure is enough for this simplified version that we're dealing with. So yeah, kind of that's what I was saying before, that you can think about and the other name that became very used by algebraicists and algebraic logicians is residuated monoids, or and they've liked the names exponential monoid, but I think, you know, we all kind of agree that that's what we're talking about. And you know, the first thing to think about is, you know, we're dealing with 2, we could do with 3, and that would give you some sort of Kleene-like language where you have that things are related, not related, or we don't know, we are uncertain. You can go for all sorts of multi-valued logic if you so wish, but then you can do the more exciting stuff, because you can think about the lineal that corresponds to the interval, the real closed interval between 0 and 1, and you know, that is a lineal too, and as is the positive, the natural numbers and stuff like that. And this all kind of will give you different kinds of nets, and moreover, you can put those nets together. You know, you can have a net that actually has different arcs for these different versions of lineals, which I hope we'll see in a minute. So what you need to do is you need to code up this notion of how the transitions happen, how your tokens move along your net in terms of this pre and post conditions. And that was the very good initial idea of Brown and Gurr in 1990, was exactly to say, oh, okay, if it is a net and if it has a transition function, then I can just rewrite that in terms of pre and post conditions. And so we are back to the lovely descriptions of Elena, and you see that she starts directly from the lineal and explaining what a lineal is, kind of as a monoidal closed poset. And kind of the discussion that we just had about how the instead of having a commutative square here, we have a commutative square up to the relaxing of the alphas and betas in the direction of one being less than equal to the other, which you can read logically as one implying the other. And then you kind of start playing with specific nets, or Elena starts playing with the specific nets, and shows that the first thing that the technical report showed was that the natural numbers with addition, 0, and truncated subtraction is a lineal. And, you know, for people who hadn't seen this before, this is just one of the easy consequences of Bulovier's paper on ultrametric spaces and stuff like that. It's one of the subsection of his paper, is this idea that that natural numbers can be thought of as a lineal so long as you use truncated subtraction, and so long as you use the opposite of the normal order on the natural numbers. So using this idea of a lineal, you can start kind of, and another bit of useful notation is that instead of writing pre and post, which are bit of long things, you kind of start using the relations alpha with these little dots. The dot before the alpha kind of says pre, and the dot after the alpha is for post. And then you can just try to calculate like a normal human being using 1s, 2s, and 3s and 4s and stuff like that. And then you see clearly that the way we described the dialectical construction, this is just a dial n of sets. And then, sorry, before kind of going for the linear logical constructions, which I should, how we're doing in time, we're good. So before going for the dialectical constructions, we can look at this idea that, you see, if the dialectica is a construction that takes a category C and then does a dial sub L of C, you have at least 3 parameters to play with, right? You can change the lineal, you can change the category over which you're doing the dialectical construction. Oh boy, sorry about that. What happened here? Your screen sharing is paused. Sorry, I think the best thing to stop sharing and start again. Hang on. Where is it? Terribly sorry for that. I do not know where what happened is that the telephone kind of came into the computer instead of going to the telephone, and now I do not know where the where the PDF that I was sharing with you has gone. Sorry. Well, I know where it is. Oh boy, I'm so sorry. Can't even find the email that I sent myself for and Toby. Okay, I found it. Sorry about that. Okay, now share. Oh,
Valeria.
Yes.
Once you get to the slide, can I ask a question?
Sure. I mean, it came out, but what happened was that, let me try again. No, it was bad. It's just that there was 2 different views of so sorry, because it does not seem to be looking at the, found it again, I think. So yeah, we're kind of writing. Can you see it now? Is it working for you?
Yep.
Okay, so, but now I have people underneath my screen and I don't know what to, okay. I need to kind of change where people are sitting on my screen. Otherwise I can't see the, okay. Right.
Can I ask a question before you move on?
No, go ahead. Yes, please.
So the morphisms were forward on the U's and backwards on the X's. Is that right? And if so, can you say what that means in terms of or what's kind of happening with that in this picture?
You know, the interpretation here is that you're sending events to events, and the conditions kind of go backwards because they have to do this business of thinking of both preconditions and postconditions. Let's kind of, I mean, I'm going to come now to examples that are more of this size, this kind of size. So I think you might see better then. Hang on just a sec.
Great, thanks.
So say you wanted to do a Cartesian product of these things, and using the kind of notation that I was saying was Elena and Vilma's idea to kind of, I mean, actually the original way of using this dots was actually Glenn Winskill, but they kind of decided that they wanted to use it here. You can see that what you do is you think about the events that are they use as the boxes, and you do the Cartesian product of that, and for the conditions, when you're doing Cartesian product, you have to use a co-product in the conditions. So you start kind of collecting things with different indices to know where they're coming from. So in reality, the Cartesian product and the Cartesian co-product are very easy to do in this sort of nets, because some of the things come with the place where they are happening. So they don't need to, you don't have to multiply it completely. But other things like the monoidle product, that one kind of really becomes gigantic, because you have to create this carrier which has not only the Cartesian products of the events, but also function spaces for the conditions, and with this characteristic that, you know, David, you particularly should be thinking of this this monoidal structure that I think you also have in the polynomials, which is a cross product, right? Because you see the original net was U and X, and the other original net was V and Y. But the new one that we construct for this monoidal product, which will be the monoidal product of the adjunction, it has this cross dependence that makes the second net go into the conditions of the first net, and the events of the first net go into the conditions of the second net. And so we still have to satisfy, I mean, you have to use evaluation at the points U and V, which you have because you have the product here. So you can do evaluation to obtain a real natural number on the after doing this. Okay, let me say it in a slightly better way, perhaps. What you're doing is you have these two relations, one alpha and one beta, one relating U's to X's, the other one relating V's to Y's, and you created a whole function space of this stuff, but you applied it to a single point, a little U, little V, and hence, you know, what you're doing is you are using the monoidal structure of the lineal, and because that's what this plus coming from is the fact that this guy here is a natural number, this other guy is another natural number, and you are adding them. And that's why we're kind of just doing it very small examples here. So this one kind of just one event, two events, and two conditions to show that to show how this happens in N. I mean, I hope that looks a little bit better, but if not, ask more. And the essential bit, the bit that was desired from the point of view of logic, but slightly more complicated from the point of view of category theory, was to actually getting the internal home to work the way it needed to work with that monoidal structure. So the way I say it normally is that the original Dialectica, the one that has the parameterized extra component, that one came from the notion of implication in Gödel's idea. And then you had a very easy monoidal structure that made an adjunction work on that case. In this case, you simplify the function space between the two objects, but when you simplify the function space between the two objects, you complicate, I mean, and it's not simple, right? It's still fairly complicated because it's still kind of going from u's to v's and from y's to x, so things that go kind of proofs down there, counterexamples going up that way. And kind of what was hard was to think, okay, for that, we need a monoidal structure like the one that we just saw here, which kind of does the same sort of function spaces on the kind of counter examples side, and simply has pairs on the proof side. So you see, this was kind of calculated, taking the adjunction as the basic thing and trying to discover how to make the adjunction work. And it is kind of surprising that when you look at it in terms of the nets, you do get to see a notion of refinement, or a notion of simulation, perhaps, between the two nets. And I mean, I find it surprising that people did see that happening. And I kind of going to try to go over some of these examples, because I think what happened was that people decided that the examples and the possibilities of applications of examples were the important things in the work. In particular, I think Wilmer, kind of, who is more of a chemist himself, is very excited about using these different notions of lineals to think about what he calls the chemical space. So, you know, I think I passed too fast over a bit where I was saying that you wanted to have multiplicities, and you wanted, for instance, to say things like, you know, you have H2, two H2s plus one O2, so that you can produce two molecules of H2O, which is water. And this, what Wilmer tells me, is that they have, the chemists have been kind of creating these recipes on recipes of how to construct compounds, not only at the level of molecules, much more at the level of real compounds, of chemical compounds, for many, many years. And, you know, on this chemical space that they have, they want to have this kinds of, they want to write the things as Petri Nets with different kinds of arcs. So they want the multiplicity arcs, because of, you know, you need to know how much of one resource is versus how much of the other resource. You want to do it with probabilities when you don't know for a fact that it is two H2s and one O2. You want, according to Wilmer, which I never heard of before, but you want to deal with things like inhibitor arcs, kind of saying that the net's working like so, but, you know, it only works if one special arc is inhibited by the system. the environment in which you are kind of trying to make this compound, and you know, the rates are similar things. That's more how the chemical space behaves, and he thinks that he can look at trends in this chemical space and see how how you can put together, which is the kind of bit that that they find most exciting about this work, is this idea that you can put different lineals together in the same net, and that means that some of the transitions will happen on this mode of probabilities, and the other ones are going to happen in the mode of deterministic multiplicity things. And so that's the hope for the application side of this work. And I think they have very specific, I mean, if you go and look at the archive, we have the paper written from the ACT, and that has just been submitted. And there you're going to see that some specific, I mean, each section, some of the sections have specific examples, like this minimal circadian clock model, where I don't remember anymore if this is an inhibitor arc or not, or kind of, I think this one is a rate versus kind of things that have numbers to them. And yes, and this whole thing, for instance, happens over the lineal 3, because you don't know, I mean, you have arcs that exist for sure, arcs that you know don't exist, and you have this uncertain arcs that that are important for this modeling. Again, I think the probabilistic versions are the most exciting, and here the problem is an embarrassment of riches, because there is an awful lot of different people using different kinds of probability theory for their kinds of nets. So we kind of chose the one that makes sense from the logic point of view, to make it kind of, as I was saying, a symmetric monoidal closed category, and which will be a star autonomous category and stuff. It won't be the star, it's going to be an autonomous category. It's a symmetric monoidal closed category. The duality thing can be done, but we haven't put any effort into that. And yes, we kind of use kind of truncated subtraction with the rates for some of the examples in the paper, inhibitors and stuff, and products. So summing up, Wilmer and others think that the main gain that we got was this different kinds of arcs labeling the same net. We kind of have a compositional theory from the beginning, because we actually chose to start from category theory, and we kind of stuck to the linear logic connectives from the beginning, with one big exception, which is that we always knew how to do the modality that brings the linear logic to the intuitionistic logic, but we never bothered to do that because the things are too big, and we would, I mean, and for doing the pling, the shriek, the modality, things get even bigger. So we didn't bother with that. And it's always in the back of my mind if that's a necessary, if we should be doing that. And I think I kind of want to stop here and kind of just discuss a little bit with people, if people have this the disposition, about the several different directions that I see for improvements and modifications of this stuff, because the actual use of the nets, as I was saying, carries on, but it's much more about the dynamic, what I wanted to finish on, and I didn't produce a slide for that because I don't know how to draw it. But I wanted to end up on this idea that the nets here are a little bit like, I mean, they're mostly their graphs. They are bipartite graphs with arcs that are labeled by a logical structure. And the other side but the reason why people invented Petri Nets is to actually think about the dynamic behavior. So it's about how whenever you put different tokens on a same net, things will kind of shape up differently. Different results will come depending on how you distribute your original tokens on the net. And that we don't have much to say. If you see what I mean, our kind of theory of nets is much more about the fixed structure over which things run. And, it might be very helpful to kind of investigate the space, the chemical space, through the times, through, all the recipes that the guys already produced since the 1800s. But it's not very good to think about how you can use the nets to predict newer things. It's about descriptions. It's not about the predictions of what will happen next. And on that, I think I will stop and talk more to people. Thank you.
Okay, thanks, Valeria. So before we take questions, well, maybe I'll start with a question. Can you show us again the monoidal closed structure? Sure. I got the monoidal product of the powers. Maybe if you could go back.
I think you can see the internal home.
Yeah, there. The next page.
That's the monoidal, and
that one I get.
That you got. This one, you see, it is very much. It's very much like the monoidal. Look at them side by side. The only difference is that in the monoidal side, the easy side is the side of the events, and the complicated side is the side of the conditions, whereas the internal home, it's the other side, right? Because, an internal home has to be a function that goes from u to v and a function that goes from the y to x. So this is just kind of internalizing a map from alpha to beta. And then you say, well, but, to kind of, if I have the internal homes there already, I need to actually evaluate them into the objects. And you see, it's here, the objects that we're evaluating at are already one on the side of the events and the other one on the side of conditions. So they're not.
Yeah. Actually, so before you get to the alphas and the betas, aren't the alphas and betas already, aren't the two alphas already part of the UV or UX? Sorry, the alpha beta thing.
We do have to apply alphas and betas to elements, right? So we have to look at the sides, and here we're kind of thinking that this truncated subtraction in N is the version. So let me put it again in a different way. You have a little bit of logic on your L, and in this case, we're saying that the L is natural numbers plus of natural numbers, so 3 plus 3, 6, and truncated subtraction does the internal home sort of thing, which is the Lovier original idea. And that's what is happening in the N and then which is the lineal in this case. On the outside, what is happening is just this business of kind of true space-like thing, where you have on the left side, which are in the logic is the proofs, and the right side in the logic is the counterexamples. In the nets, on the left side is the events, and the right side is the conditions. And the thing that is happening in terms of the monoidal structure, or the closed structure, is that you're just internalizing what you decided should be the notion of a map between two such things. So I think what you should be thinking of is that the alphas and betas are all pres and posts, right? And you have to have you have to double your effort, because you have to have a pre and a post just to do the description of the net itself.
Great, thank you. I think I'm starting to understand. But we can talk more, I guess, in person.
We can talk.
So other questions?
Eric Bond saying on the chat that the directionality of the arrows are similar to the consequence pre and consequence post rules in Hall logic. Absolutely. That's kind of where they come from, sort of, right? I think the order of the things comes as that Hall kind of had a pro and post, and then Glenn Winscoe kind of used that in his nets, and we are just kind of using Glenn's idea for those nets. But whenever you have to make a decision, and lots of times you have to make decisions, we went for the more logical decision because of this overriding attempt long time ago to see linear logic as a logic of concurrency. But yeah, you're right, Eric.
Great. Any other questions?
May I make a question? Ask a question?
Sure.
So you showed that the lineal of like the unit interval gives you probabilistic Petri nets, right?
Yes, I did.
So are transitions there enforced to be like unitary in some sense, like in the sense that the probability that all the possible transitions in a given configuration add up to one?
I think so, but I'm not absolutely sure. I think, you see, that's, I kind of paused a little bit there to say that we were kind of following someone else's version of the probabilities event. So kind of, I would have to open to cheat and open from my own archive paper to see which one of those, because we discussed a collection of those, trying to find the one that would, as I was saying, make good on the logic front. I think normally people do try to normalize the events and have the things adding up to one, but so that you can keep the 2 points, right? The zero and the true as fixed things, and have the other things in the middle, but adding to one. And I think we did find one, but I'm not absolutely sure. I don't know if the guys are here. I think they are not. If they, I mean, I can come back to you on that, but you can also have a look at the archive, yeah. The preprint, sorry. But I think we did find one that, you see, this is kind of very funny because the idea was exact. I mean, my idea originally was very different from the idea of the people in the group. I kind of wanted to choose one of these lineals and go for it. So in particular, I wanted to choose that one, the probability one, because as I say, I think most people who are using still Petri Nets are using it probabilistically. And so we looked at 3 or 4 kind of examples of different practitioners, people who did not have a category in sight on their papers. They're just doing stuff with it. And we kind of, and we had this difficulty because I think one of the papers that we read said something like, oh, there are 8 different structures that we could and sometimes use here. And you know, that was a very short paper, just descriptive of what the kinds of models that they were using, and I think they had 6 or 8 of their own. And at some stage I was so many examples that kind of didn't agree with each other that I think Elena said something like, no, Valeria, nothing's going to work, you know, it doesn't work, it's just, there's no point. And then we had a longer conversation, and I tried to find other friends to help convince her, and kind of did get someone to kind of say, no, this one here does work, because for me it was very important that the logic worked too. It might be silly in the long run, as I was saying. My main goal nowadays is to get the users to like it. You know, kind of our lives as people who want to have models are hard enough. You know, you should try to get as much as possible the things that people have a good feeling about. So, and you know, and I have to admit that the morphisms in my sort of systems are too big. They are too unconstrained in some ways. So I tried to I would like to kind of choose one and stick to it and just use one in real life and see if we can get more useful results instead of just mathematical niceties. But yeah, I haven't done that.
Okay, thanks for the question. I think we should stop there and thank Valeria again. So thanks again.
Thank you.
And we'll stop the live stream and the recording, and then we'll anybody who wants to stick around and ask more questions is free to do so.